presentation now, but we will now go on to have a full specification of the Bayesian network, including all the parameters. So we're interested in the joint probability of capital X represents the sequence of all observations, and Z is the sequence of all hidden states that gave rise to those observations for some parameterization of the model, where parameters comprise the following. We need, on one hand, a parameter that tells us at the very first stage, what is the prior distribution over the hidden states. So this is the vector pi. Then we have the matrix of transition probabilities A, and we have factors that parameterize the emission probabilities. So let's say, given that we are overtaking if that is the true hidden state, what is the probability of having an indicator on having the gas pedal pressed down and so on? Okay, and as I said before, these parameters are assumed constant over time, which is another great simplification. Okay, now this probability, so just to be more explicit, capital X means all observations from the first to the last. Capital Z means all hidden states from the first to the last. And now we can invoke all these conditional independence relations that are expressed in this very sparse graphical model. So we have, on the one hand, the probability of the first observation, which depends on the hidden state at the first time step and on these emission factors. Then we have the prior probability of being in a particular hidden state at the first time step, which is parameterized by pi. And then we have repeatedly, on the one hand, the probability of making an observation given the current hidden state. Probability of making observation xm given hidden state zm and our emission factors. And in addition, the probability of a given hidden state conditioned on the previous one. And that depends on this matrix A of transition probabilities. And we can now look at each of these terms in turn. So, well, the first one is easy. Let's look at the second one. We assume that we have a total of capital K possible states. And this is summarized as pi k. And we have now used an indicator variable, 1 of n coding. So So what I mean by that is that each znk can only be 0 or 1. And since we have only exactly one hidden state that is active at a given time, we have this constraint that summing over all states k just one of these, or exactly one of these indicator variables must be 1. Okay, and this is the indicator variable that was used here. So pi k would be the probability that our first hidden state is state number k, and then we take this to the power of this indicator variable to this amount to picking one element. All right, and because this is a probability, we have the constraint that the sum over these pi k's must be 1. Then next interesting term is that one here. So we have the probability of xn given zn and phi. Where again this indicator variable is used, and this distribution here is typically a multinomial or a multivariate normal, or even a mixture of Gaussians. Okay, and the last interesting term is that one here. So the probability of Zn given Cn minus 1 and A is, and now we have a double product over all the possible states j that we could have been in at time t minus 1, and all the possible states k that we could be in at time n. And then this is taken to the power of z n minus 1j, and this is taken to the power of znk. So again, picking one element.
Sorry, could you explain again what P, A, and phi are?
Sure. So A is the matrix of transition probabilities. So let's say, given that I'm in state stop, how likely is it that I go to any of the other states? So I would have a diagonal element that describes how likely it is to go to stop when I am currently in stop. I would have an off-diagonal element, let's say, 0.2 chance or so to go from stop to accelerate, and all other entries in that particular row would be 0, because I cannot go anywhere else from the stop state. So that's the transition matrix. Then pi gives me the probability of finding myself in a given hidden state at time 0. So for instance, I have created these two time series, both starting in the stop position. Let's say I draw more time series from this model, and if each and every one starts with a stop condition, then I would know that the prior probability as encoded by pi tells me that at the very first stage I have a certainty of always starting at stop and not at one of the other states. So pi gives me the distribution at the first time step over those possible different hidden states. And phi makes the connection between these hidden states and the observations. So how probable is it, for instance, to have the gas pedal step down and the indicator on, given that the hidden state is stop? Not very likely. But how likely is it to have the gas pedal pressed down and the indicator on, given that I'm currently overtaking? That would have a much greater chance. And not likely or very likely and so on. This is encoded by these factors phi. So those are the emission probabilities. So this term would be the emission probability, and that term would be the transition probability. So the emission probability of observation given hidden state, and the transition probability from previous hidden state to current hidden state. Okay? All right, and because this is a transition matrix, we have constraints that each element of this transition matrix must be between 0 and 1, and it should be stochastic. So the row sum should be 1. Or in other words, the chances, let's say we have a 0.8 chance of staying in stop and a 0.2 chance of accelerating. So these numbers, they must always add up to 1. Okay. I will summarize what was written there for later reference in terms of these abbreviations that have been introduced. So overall, this probability of a sequence of observations and a sequence of hidden states given the current parametrization, or I could write explicitly, so given pi and a and phi is given by, and I'm just rewriting the same thing but with these abbreviations. sorry, there's an ln missing here. I've taken the normal logarithm of this probability. And because I'm taking the ln, I can take the exponents down as multipliers. And write these products as sums. So if you want, give this equation a number because we will need it again. Okay, so, well, the hidden states are hidden. In other words, what's really more interesting is to have just the marginal probability of x under a given model. So I should really write x given a certain parametrization, but I will omit this just to be a bit shorter in all the formula here. And HMMs have been most widely used or popularized in speech recognition. So, for example, x could be the recording of a spoken utterance, and then we could have parameters that correspond to one given word. So let's say, these nasty systems, you try to call, let's say, the rail, and you don't have a human operator, but some machine asking you, would you like the main menu, then please say 1, or would you like to never call us again, and say 2, and so on. And then you say something, and they hopefully recognize it. And typically, there's an HMM sitting on the other side. So let's say, for example, that we have the probability of the recording under a model which has been parametrized to recognize the utterance 1, but there has been another model that has been parametrized to recognize the utterance 2, and so on. And then you would ask yourself, which of these marginal probabilities is highest? And if your recording has the greatest probability given the parameters of the word 4, then you would guess that the person has probably said 4. Okay? And in speech recognition, by the way, these models are typically a bit less complicated than the one you see here, because these utterances, so I'm unfortunately bad at phonetic language, but the phonetic, if you write phonetically 1, then you probably have something like wa and a and n. And those better educated than I can replace this with the proper symbols. And you would now try and interpret this recording. You would now try and interpret this recording that you have in terms of this sequence here. So, for instance, if somebody says 1, then you need a lot more cycles here on the wa. If somebody has been very short, 1, then you had very, very few recursions. And this is one of the nice things about hidden Markov models, that they're relatively flexible with respect to the length of signals. So they can be used to abstract from, to some extent, from, let's say, different pronunciations of how long somebody expresses a word. So let's say for 7, again, I cannot do this in phonetic language, but we would have an S and an E and a V. And so if somebody truly said 1, but we have plugged it into this model here, 7, it will get a probability, but it will hopefully be much lower than the one under the correct parameterization. And this is the idea, basically, how speech recognition works. What I've omitted here is I have not talked about the observations at all, only about the hidden states. In speech recognition, people typically use a cepstral representation. So essentially, they use windowed Fourier transforms of the original recording and then have each of these hidden states map to this space of spectral densities and to see if you get a good match of your current moment in the utterance and the current hidden state that you are assuming. So these models here are called left to right HMMs because you can only visit the state itself or continue to the next state. So in other words, the trellis diagrams, they become much simpler than the one you've seen here. So you can only stay in the same state or go on to the next one. Okay, now this was a long explanation of why we want to be able to compute the probability of X. And since we're just talking about one model now and not many different models, I'm going to omit this reference to the parameter vector, and I will simply write that I'm interested in the probability of the observations in the current model, which I obtain by marginalizing out the hidden states. And for instance, I could start from the joint distribution of all observations and the final hidden state. So this is a small z because I'm only looking at one hidden state, namely the final one. And I need to sum over these possible final hidden states. All right, now this term here, probability of all observations and the final hidden state. We're going to encounter this frequently, which is why it has it gets yet another name of its own. This field abounds with abbreviations. I'm sorry for that, but writing it out would be even harder. So this is the definition of alpha of Zn. And now we can use these conditional independencies to say that we have, on the one hand, sorry, those should be, I'm not doing this for the final n now, but for any n, so this should be just a small n. So any n and not just the final one. Okay. Now I'm rewriting this as the probability of xn, which depends only on the current hidden state, and a summation over possible hidden states at the time instance before. The transition probability. Which, if you look at this definition here, is just alpha of Zn minus 1. So how did we get this formula? Perhaps I should do this in more detail. I can rewrite the expression as the probability of xn given x1 up to xn minus 1 and Zn times the probability of x1 up to xn minus 1 and Zn. So this equality I'm getting from up there by just saying that joint probability of variables A and B is the same as A conditioning on B times the probability of B. So I'm using this rule here where this xn amounts to A, not the transition matrix, but just the symbol A, and that amounts to B. Then by the conditional independence assumption, so if you look at the D separation in the graph, this is just xn given by Zn. All the previous observations have no information. So if you remember the discussion about D separation, I'm interested in the distribution of this variable given that, and that because this is observed, it blocks this path, so it's de-separated from all the other previous observations. Okay, so this is the first term. And now let's see about the second one. I can again write this as marginalizing out of the joint of px1 given x minus 1 and Zn minus 1 and Zn. So all of that gives me this. And if I now use same relation again, I find that if I already condition on Zn minus 1, Zn no longer holds any. Let's do this explicitly. should do it the other way around, sorry. It's correct, but it won't give us this expression here. So what I do want is okay. Now, by the deseparation criterion, I can omit all of these. I can forget about all of these x's, and what I'm left with is this term here, and that is that term there. Okay, so I've written these lines just to show that this line is actually true. Okay, so let's. Third line is which one? This one here? No, we're looking at this term here. Huh? So we start here, and there's no summation there. Ah, okay. Good. So let's say this is equation number 1, 2, 3, 4, 5, and from these follows equation 6. Good. Okay, so overall, because this is important, let me write this again. Overall, we have that alpha of Zn, which is an abbreviation for, as defined there, is probability x and given Zn times the sum over the hidden state at Zn minus 1. This is the transition from Zn minus 1 to Zn. And there we have again alpha. Okay, because alpha appears both left and right of the equality, this is why we have a recursion. This is called the forward recursion. Or we will later see that this is actually a forward message passing. Now we will introduce a few more abbreviations because sometimes we might need, or we will actually need later on, the probability, the marginal probability of a particular hidden state at time n, given all observations. And because this will be a recurring term, it gets an abbreviation of its own. This is gamma of Zn. And just by the rules of probability, this is the same as the joint of x and Zn divided by the probability of x. So you see, if you multiply by x, then I think you will agree that this is true. And I will now partition this into two sets here. On the one hand, the probability of the observations n plus 1 to the end. So the reason for this equality is just the one that we had before. So the probability of A times B is the probability of A given B times the probability of B. Okay, that being A and that being B. And we can now again exploit the conditional independencies and write merely that x n plus 1 up to x n depends on Zn, but not on the earlier observations. And this is a term we've encountered before. This is just alpha of Zn. And this one is also going to appear a few times, which is why it's got a name of its own. This is beta of Zn. And P of x can be computed conveniently by just summing over the different Zn's by summing over the hidden states at a given time. So okay, and to finish off with alpha and beta, as the last thing before the break, we will also derive a recursion for this beta, because it turns out that we will need this factor later on. So beta of Zn is defined as the observations at times n1 up to the end, conditioned on the hidden state at time n. And we rewrite this in terms of the joint probability of the variables that I've just named, as well as the hidden state at time n plus 1. And we're marginalizing this newly introduced variable out. And then I will first condition on this newly introduced variable, and then multiply with the conditional probability of this new variable. And this can be factorized as follows. So we have the probability of this observation x at n plus 1, which depends only on the hidden state, times n plus 1, whereas all other observations only depend on Zn plus 1. And I just carry over the last term like that. And this one turns out to be again beta, but this time evaluated at Zn plus 1 rather than at Zn. Okay, and again we have a beta here, and we have a beta there. So it's again a recursion, this time a backward recursion or backward message. Backward because we're starting from the end of the chain and computing beta of Zn in terms of beta, an element that is further to the right, beta of Zn plus 1, and so on. So we recurse from the end towards time number n. Okay, so no more new abbreviations for the next 3 pages, and then a few more. So it turns out that these recursions allow us to compute such marginals in a much simplified fashion, because if we did it naively, we would have to sum over all the possible sequences of hidden states that have given rise to a set of observations. And so not just the different hidden states at each time, but all the sequences of hidden states. So if we have a series of observations, it could be that it was generated from this sequence, but it could be generated from that sequence or from one of the exponentially many other sequences that you can generate from such a model. And these recursions, they will strongly remind you of the message passing that we've seen of dynamic programming. So they allow us to play a trick and beat the computational complexity of the problem. And these recursions are at the heart of why hidden Markov models are so popular and so successful, because they are tractable. And this is also why people have applied them to so many different problems. On the one hand, they're quite powerful for modeling, but on the other hand, when you have a hammer, then everything looks like a nail. And this turns out to be a very good hammer. So it's used a lot, not only in speech recognition, but also in bioinformatics and decision support systems of all kinds. Okay, more on that after the break.